So the idea is we can run VPN on Cisco routers. We can also set up VPN services through Cisco firewall device called the Cisco ASA. Now, for the mobile users, doing IPsec encryption, remember the clients would need to have some kind of IPsec VPN client software. Okay, so in the old days, Cisco does provide a sorry about the old days. So Cisco does have a VPN client software that you can install onto your users to allow you to do IPsec encryption for mobile devices. Okay, but many years ago, when the mobile devices are still using very lousy CPU chips, okay, we found that when they try to do IPsec, okay, it creates too much latency. It created too much latency because the handheld devices do not have enough power CPU to encrypt and decrypt the data efficiently. Now, Cisco also comes out with this device called the Cisco Hardware Client to cater to legacy devices. Well, this is particularly in the education sector in the US. Now, in Singapore, our schools usually have the latest and greatest computer in their school premises. But in the US, where education budgets are slashed left to right, so there's a lot of legacy machines that does not have this encryption capability, or Cisco do not have software for them. So what Cisco did is to come up with like a proxy box whereby it will do all the encryption decryption on behalf of those old devices that either doesn't have enough CPU or doesn't have the software support to do encryption by themselves. So this Cisco hardware client box, which is like a encryption proxy box, can do all this encryption and decryption on their behalf. But of course, Cisco is not stupid, so they put an artificial limit of 8 PCs so that this proxy box can only support 8 legacy devices, because if not you might wind up plugging 1000 PCs to use this Cisco hardware client to do encryption decryption services. So Cisco artificially limits this to 8 PCs. So remember, there are two kinds of VPN connections, IPsec and SSL VPN. So IPsec is layer 3 in the sense that it is application independent, whereas SSL, in the classical SSL, it is application specific because it's tied to HTTP, browser encryption. So you must be using a browser in order to do SSL encryption decryption. That's the classical distinction. So in this slide we're going to talk about layer 3 IPsec VPN. Now, in order for IPsec to do its job, okay, so IPsec offers a open standard, okay, an open standard to make sure that the data is confidential through the use of encryption. The data integrity means that along the way we must make sure that nobody tries to modify the data, so we can have some kind of checksum, or what the technical term is called hashing, but you can think of it as some kind of CRC checking. Checksum that produces a unique fingerprint to these strings of ones and zero being sent across the network. And IPsec will also guarantee origin authentication. So we have to use some kind of authentication to make sure that we are communicating with the right device through the use of authentication. So this is the three things that IPsec has to deliver: encryption, hashing to make sure that nobody modified the data, and authentication. Make sure that you're talking, encrypting, decrypting with the right end devices. So IPsec provides confidentiality, and this is achieved through the use of encryption. Data integrity, this is achieved by using some kind of hashing. Okay, checksum, if you think of it as checksum. And how do you know whether you are talking to the right person? We have to use the idea of authentication. Okay, and IPsec provides the idea of anti-play protection. Okay, so this one is mentioned but not really highlighted too much in the class. Okay, so in this class we mainly talk about confidentiality, integrity, and authentication. So how to provide confidentiality? Well, the data has to be encrypted. So as you send things through the shared infrastructure like the internet, to prevent other people from seeing your data, okay, the data is encrypted. So even though somebody else, non-authorized person, managed to pick up this data, the data is in gibberish. They will not be able to understand what the data represents. Only the authorized user that has the key to decrypt the data, they will be able to unlock the data, decrypt the data, to see what the data is trying to say. So this brings up the point that, okay, so when you do encryption, we need to figure out what kind of encryption to use. There is the single dash encryption, triple dash encryption, and the AES encryption, or the RSA encryption. So there are various different types of encryptions that you can use to encrypt the data. So single dash is not as secure as triple dash, and AES is currently the most powerful encryption services available. So when you want to implement IPsec on your Cisco devices, you have to get Cisco to give you the keys to enable those encryption algorithms, because those encryption algorithms are export control. So certain terrorist countries are not allowed to have those advanced encryption algorithms in their devices. So as we have learned from the previous slide, that there are different encryption algorithms that we can use: single dash, triple dash, and AES. Different CPU requirement. Okay, but all these encryption have something in common, in the sense that they need a key, okay, in order for them to do encryption decryption. So how do you send this key, how do you send this encryption decryption key securely to your peer router? Well, one way is to do what we call external means. So for example, you use FedEx, whatever, some kind of external means of sending the keys to each other. Well, it is possible, but it's very um, inefficient, right? So is there any way to send the key securely to the other peer through this shared infrastructure that we are connected with? Well, it turns out that Diffie-Hellman came up with the solution. His idea is to send half a key. So what happens is each peer router or each peer encrypting devices will come out with a private key, and from the private key they will generate a public key. Private key, public key. Okay, now the private key is never shared with anyone, but the private key is never shared with anyone, and the public key is being sent out through the shared infrastructure to each peer. So only half a key, the public key, is being sent through the shared infrastructure. Now through advanced mathematics, the local private key combined with the remote public key, the local private key combined with the remote public key, they are able to produce the same encryption keys back on both sides. So this is called the Diffie-Hellman solution. So by sending half a key through the infrastructure, the shared infrastructure, people will never be able to generate the encryption key, because they are never given the private key. And through advanced mathematics, the local private key and the remote public key can be combined together to form up the same composite encryption key. So Diffie-Hellman comes in a few flavors: DH1, DH2, and DH5. Now, to keep things simple, just think of it as when you are setting up the Diffie-Hellman 1, Diffie-Hellman 2, or Diffie-Hellman 5, think of it as setting up the length of the encryption key. The length of the encryption key. The longer the encryption key, the more secure the key is. The longer the key, the more secure the key.